Hello and welcome to another episode of Science with John. My name is John and today we're going to be talking about transformers. We're going to go over the what, the why, the how of transformers, and then we're going to run some practice problems. Hopefully by the end of this video you guys are going to be experts, and with your help and my knowledge we're going to be unstoppable. So let's get started. Let's talk about the what. What are transformers? I guess before we start, I just want to apologize. There's some people playing basketball outside. You might hear them. BYU beat Gonzaga, so everyone is pretty hyped around here. It doesn't happen too much. This is Provo, but we're going to go with it. We're happy. So let's talk about the what. What are transformers? So here I've kind of given you a broad overview. Basically what a transformer does is transforms. That makes sense, right? So a transformer transforms volts from high to low or low to high. So I kind of drew a diagram here. The first thing is a power plant. We have a power plant and we've got a certain voltage coming out of this power plant. Let's just say it's like 12 kilovolts. And then what we want to do is we want to get that voltage all the way to this house over here, and we want it to be at about 240 volts. So how are we going to do that? Well, the first thing we need to do is get it all the way over there, and if we want to transport it, we got to increase the voltage. We'll talk about that in a second. So we want to step up the amount of voltage. We want to increase the voltage, and we do that through what is called a transformer. You know, transformers transform volts from high to low, in this case, low to high, right? And so that's going to transform it to about 400 kilovolts, and then after we have the volts there, we're going to transform it. We're going to bring it back down through this step-down transformer to about 13 kilovolts. And then we have yet another transformer here. It's another step-down transformer, and that brings it down to our final voltage, 240 volts, which we use in our homes. So that's kind of an example of what transformers are. You see, we're going from medium voltage to a high voltage to another medium voltage to finally a low voltage. Now, why do we do that? Why do we have transformers? Well, there are a couple reasons. The first reason that I can think of is low energy loss. So when we have a higher voltage, like in this case 400 kilovolts, why would we ever want to do that? Well, when we have high voltage, that means we have low current. Low current means low resistance, and then low resistance means low energy loss. So for these power companies, they can transport this electricity with minimal and this power with minimal energy loss, which is very important. They can use kind of thinner wires and helps them out a lot. The second reason is sometimes we need lower voltage. Lower voltage is safer and usable. So kind of every different appliance and sort of system that we have uses a different amount of volts to power whatever it is that it does. And so here are a couple examples. We have cell phones, laptops, video games, appliances. All of these things use volts, and they use a different amount of volts than the other thing. And so we've created this machine, or not really a machine, this system that transforms volts from high to low or low to high to give you the wanted voltage. So how does that work? Well, the first thing that we need to understand is Faraday's law of induction. Faraday's law of induction basically tells us that EMF or voltage, right? Oh, I'm sorry, I just erased that. Let's not do that. I meant to circle that. So the EMF or the voltage, this is your induced voltage, comes from what is known as a change in magnetic flux over change in time. Now, don't worry too much about this right now. I'm just trying to explain this concept so you can have a basic understanding of this. And that change in magnetic flux over the change of time induces what is called an EMF. And the more number n, or the more number of loops that we have, the greater the EMF is going to be. You're probably thinking, why is this guy talking about loops, changing magnetic flux? Like, what does all of that mean? Well, as you can see in that picture on the bottom, there's a transformer and it's got some loops. And so we're going to be talking about how the number of loops relates to this induced EMF or this voltage and how that all works. So just trying to get you to understand that transformers, they rely on EMF produced by alternating current. And so The same thing that Faraday was teaching with his law of induction is true in transformers, right? So transformers are usually supplied by what is an AC current. In transformers, we never use DC current. I guess sometimes you can. I was reading a little bit about that, but it's very rare. Almost never happens. You have to do some weird stuff. So we're going to focus on AC current. AC current means alternating current. That just means the magnetic field, the magnetic flux is always changing, and when it's changing, we're going to have an induced EMF, and that's important. So transformers are constructed in the way that you can see in that figure in the upper left corner of the screen. They've got two coils. As you can see, there's a coil on the left and a coil on the right. And those are kind of wrapped around the ferromagnetic core. So the reason there's a magnetic core is because that confines the magnetic field, as I wrote down here, and transmits it to the secondary coil. So the change in current in the primary induces a current in the secondary. And because transformers are constructed this way, we can make a couple conclusions. The first conclusion is right here. The change in magnetic flux over the change in time is the same. The second is there's no resistance, which means there's no power loss. Technically, there is a little bit of resistance, but it's so small that we say there's no resistance. And transformers are very, very effective, meaning there's really no power loss, okay? And so because we've concluded that, we can create a couple equations that allow us to solve problems with transformers. The first is because the change in magnetic flux over the change in time is the same, we know that the change in magnetic flux here over the change in time is the same as change in magnetic flux there over the change in time. And then we can create this equation here. Okay, don't worry too much about this stuff. I'm going through it pretty quick. You'll understand more when we go and solve some problems. So this equation is called the transformer equation, and basically what that's telling us is that the secondary voltage, as you can see here in the picture, there's a Vs on the second side. That's the volts at the output all over the volts at the primary. So Vp over there on the left side there is equal to the ratio of the number of loops on the secondary side, Ns on the right side of that drawing there, and then Np on the left side of that drawing. So the ratio of volts is equal to the ratio of the number of loops. And then the second equations, or the second set of equations, I should say, because there are a couple that we can create or find because of this no resistance here, are these. Because there's no resistance, there's no power loss. And when there's no power loss, we know that the primary power is equal to the secondary power. And then when the primary power is equal to the secondary power, we can say that the current times the voltage, which is just the equation for power, at the primary location is equal to the current times voltage at the secondary location. So, that's really cool. That allows us to draw this equation. And then if we use what we've learned here to combine it with that, we get this equation here, which is telling us that the current at the secondary over the current at the primary is equal to the number of loops at the primary over the number of loops at the secondary. So with these equations, we can conclude that if voltage increases, current decreases. You see that here, right? Like if this voltage increases, if P stays the same, then you know that this current has to decrease, right? And so that's important. We're going to be using these to solve some important problems with transformers. So let's pull up a practice problem here. Here's a problem that you'll be likely to see while you work through transformer problems. Let's pull up blue here. So the question says a plug-in transformer supplies 9 volts to a video game system. And it's asking us how many turns are in its secondary coil if its input voltage is 120 volts and the primary coil has 335 turns. Okay, so the first thing we're going to do here is we're going to write down what we know. Then we know that the input voltage, input voltage, VI, is equal to 120, or VP, that's voltage primary, is equal to 120 volts. And we know that its primary coil, or the number of loops at the primary coil, so let's see, work for me here. Number of loops at the primary coil has 335 turns. Okay, and then it also tells us that it supplies 9 volts, so the secondary voltage secondary is equal to 9 volts. Okay, so we know that we're dealing with a problem with volts and number of loops. So let's go back, let's look at our equations here. We got to find one that relates volts to number of loops. If you want to pause the video, look for it, that would be awesome, that would help you out, but I'm just going to tell you here, here's an equation where we have volts and we have number of loops. So we're going to try and use that equation to go back to our problem and solve for this question. So the equation that we pulled away was Vs all over Vp is equal to Ns all over Np. And so then we can just plug in our values. Our secondary voltage is 9 volts, right? All over our primary voltage, which is 120, is equal to the secondary number of loops, which is what we're looking for, all over the primary number of loops, which is 335. And so then we can just do some algebra. 335 times 9 volts is equal to 120 volts times Ns, right? And then we can solve for Ns, and we get Ns is equal to 25.125 loops, or 25 loops, okay? Perfect. So then let's look at the second part of that question. What is its input current when its output is 1.65? So let's get a different color for this one. We're probably going to be using some similar information, but it gave us something different. It said that the output current, no, it says that its input current, no, I'm sorry. It says what is its input current when its output current is 1.65? So we know that the final, or the IS, the secondary current is equal to 1.65 amps. 1.65 amps. Okay. So let's go back and let's look for an equation that relates amps or current with volts. So I'm just going to go ahead and use this right here. I mean, you could use this one. It's the same thing. I just like this. Let's go ahead and use that. It's a little simpler. IPVP is equal to ISVS. So IPVP is equal to ISVS. So we know we're looking for the primary current. We know that our primary voltage is 120. We know that our secondary current is 1.65 amps, and we're going to times that. Oh, what did I do here? We want to multiply those together. So our primary current times our primary voltage is equal to 1.65 amps times our secondary voltage. And our secondary voltage, as it said here, is 9 volts. So let's put that in there. And then we just do some algebra, again, to solve for IP. And we get that the primary current is equal to 0.12375 amps. Or we can just say IP is equal to 123.75 milliamps. Well, there you have it, people. We've talked about the what, we've talked about the why, the how, and we've run through some practice problems. Hopefully that helped you. That's pretty much all you need to know about transformers. If you have any more questions, I invite you to look online and try and solve those through. But I feel pretty confident that you're going to be able to work through any sort of proportionality and question that you ever be faced with transformers, and hopefully you understand a little bit better how that works. So thank you again for joining. This is Science with John. My name is John. We're signing off.